Section 6.6, solving exponential and logarithmic equations. Our objectives: solve exponential equations, and then solve logarithmic equations, and solve exponential and logarithmic inequalities. Again, those inequalities have those less than, greater than, less than or equal to, greater than or equal to symbols on them. Okay, so first we can talk about what is an exponential equation. An exponential equation is first an equation, first and foremost. It has an equal sign in it. Okay, in which the variable occurs as an exponent. For example, 3 to the x equals 27, okay, is an exponential equation. So what we're going to be doing is we're going to be solving them. We're looking for a value of the, what value of the variable makes the equation true, makes it true. Meaning, what value do I put in there makes it true, okay? So to do that, one thing we're going to be using is the property of equality for exponential equations. Basically, if I have a base, again a positive base, if b is a positive real number other than 1. So if I have a positive base other than the number 1, b to the x equals b to the y, if and only if x equals y, meaning if I have an exponent equal to just an exponent, the bases are the same, again we have the same base, then the only way they're equal is if their exponents are equal. Okay, so we're going to be using that a bit to help us solve these equations. Okay, so we're going to have a couple different methods. The first method, okay, is if you can get them to the same base. Okay. This will involve some noticing of patterns and some rewriting a bit. So here we have a 100 to the x equals 1 over 10 to the x minus 3. But I notice this 1 over 10 can be rewritten in base 10. Meaning I can write this 1 over 10 in there. I can rewrite this guy in here, 1 over 10, as 10 to the negative 1. Okay, that is the same as 1/10, but that is still to the x minus 3 power. So I was able to get this base 10. Well, I'm also able to get this over here, 100 can also be written as base 10. Just this 100 can also be written base 10. 100 base 10 is 10 to the second. Again, that's still to the x power. So all we did here is did some rewriting to get them both to the same bases. So now using my properties of exponents, a power to a power, I multiply these two things. So this would be 10 to the 2x equals, same here, I multiply this negative 1 times this whole thing. So it would be 10 to the negative 1 times x, negative 1 times negative 3, positive 3. Again, that negative has to be multiplied by both pieces. So now we have them the same base. We have 10 to the 2x equals 10 to the negative x plus 3. These can only be equal when their exponents are equal. So what we're going to do is we're going to take these exponents and set them equal to each other. So 2x equals negative x plus 3. And now we'd solve this just like a linear equation. I'm going to add the x to both sides. 3x equals 3. Divide both sides by 3. X equals 1. And then we always want to go back and check it. So I'm going to check it back in the original equation. So 100 to the first, well obviously that's 100. X equals 1. Does that equal 1/10 to the 1 minus 3? Yes, it does. They're both equal to 100. So x equals 1 worked. Okay, so that's one way. If you can get them to the same base. Okay. If you can't get them to the same base or don't know how, so here we can't get them to the same base because here we have 2 to the x equals 7. I cannot rewrite 7 base 2. I cannot rewrite 2 base 7. So we can't get them to the same base. So if I can't get them to the same base, there's two ways of working these problems. One way, so there's two ways of working this problem. We're going to do one way over here. One way is rewrite it as a log. Okay. If you remember from our previous section, log base b log base b of, let's see, let me use the same variables. Log base b of, oh, this is way back from section 6.3. Y, let's use that. Log base b of y equals x. And to write this as an exponent would be the x equals y. Okay, these mean the exact same thing. So we're going to do this to rewrite this. So this would be log base 2 of the 7 equals x. Okay, so log base 2 of the 7 equals x, because logs equal the exponent. My exponent was the x. So all we did is rewrote our exponent as a log. Okay, so log base 2 of 7 equals x. Well, hey, we've solved for x. X is equal to log base 2 of 7. Okay, we could get an approximate for this using change of base. So this is the exact answer, actually, log base 2 of 7. This is the exact answer, exact. To get the approximate, we would need to use change of base, which means I would take what the log, let's get rid of that approximately sign. I would do the log of 7, let's go base 10, divided by the log of the 2. Log of 7 divided by log of 2, which is approximately, on my calculator, I'm doing base 10, log of 7, parenthesis, divided by log of 2. We get approximately 2.807. Okay, so this means I take 2 to this power and I get 7. And so we can try it. Let's check it. If I go 2 to this number, I'm just going to go up and grab it. We do get 7. If I used my approximately, we get approximately 7, 6.998. That's pretty close to 7. Okay, so this is my approximate answer. This is my exact. Log base 2 of 7 is my exact answer. There's my approximate. So that's one way of doing it. Rewrite it as a log. Second way, our second way over here is to log both sides. It's where you do the same thing to both sides. So this is base 2. Okay, since this is base 2, I'm going to take the log of both sides, base 2. So I would take the log of this side, log base 2 of 2 to the x equals log base 2 of 7. Okay, so I have log base 2 of 2 to the x equals log base 2 of 7. If you notice, the original equation is right here. 2 to the x equals 7. The only difference is now I have a log base 2 on the side, but I had to do it to both sides. We logged both sides, because what that ends up doing is, since this is log base 2, this exponent is 2 to the x, these undo each other. Log base 2, the 2 to the x undo each other, again from a previous section, so I'm just left with x equals log base 2 of 7. Which was the same answer we had over here, log base 2 of 7. So then x would be approximately 2.807. There's the exact answer, log base 2 of 7. There's the approximately. Okay, one way, one actual real life way this is used is actually in physics, in Newton's law of cooling. Okay, so here's the crazy equation for Newton's law of cooling. Basically what this equation will tell me is it will tell me what the temperature of something is as I put it in a different environment. Meaning, if I take a 100-degree pot of boiling water and just set it on the counter, and I just leave it, how long is it going to take for the water to be 50 degrees? How long is it going to take for the water to be 20 degrees? Okay, and it all depends on the ambient room of the temperature. Okay, the ambient temperature of the room. Okay, so first, let's break down what all these variables mean. This T is the current temperature. Okay, so this is its temperature after T minutes. Okay, so this is the temp after T minutes, lowercase t minutes. If you notice, our lowercase t is right there. That's time in minutes. Okay, so how this equation works, this T sub 0, that's the initial temperature of the item, of the whatever you're taking the temp of, water or whatever. So this is the initial temperature. Okay. The R is the surrounding temperature, meaning the temperature of the room around it. Surrounding temp is the T sub R, so that's this one as well, is the surrounding temp, T of R, T of R. And then this little r, this lowercase r, is what we call the cooling rate. Every substance has a different cooling rate. Water will cool at a different rate than aluminum will. Like if you melted aluminum, it would have a different cooling rate than air, a different cooling rate than helium. So everything has a different cooling rate. So here we're cooking a stew, so we'll need to know the cooling rate of stew. When you take it off the stove, its temperature is 212 degrees. So this is my initial temp. So this right here is my T sub 0. The room temperature is 70 degrees Fahrenheit. So this is the surrounding temperature. This would be my T sub R, temperature of the room. Okay, that doesn't look like an R. T sub, they use uppercase R, temperature of the room. And the cooling rate is, so this again here is my lowercase r. How long will it take? So we're trying, how long will it take? We're trying to find the time, lowercase t. It will cool to a serving temperature of 100 degrees Fahrenheit. So how we're wanting to find T till we get a temperature of 100 degrees Fahrenheit. So this is my big T right here. Just plain T is this guy right here. So now all I need to do is use this equation. T equal T sub 0 minus T of R e to the negative RT plus T sub R, and plug everything in. So my big T is 100 degrees. My initial temperature is 212. The temperature of the room is 70. E to the negative R is 0.046. T is what we're trying to find, the lowercase t. We want to find lowercase t, finding time. Okay. So that's my lowercase t plus the temperature of the room, which is 70. Okay, so now let's simplify this a bit. 212 minus the 70, we get 142, so 100 equals 142 e to the negative 0.046 t plus 70. Okay, so now where's my variable? My variable's right in here. So our goal is to get this thing isolated because it's a thing that's got the t in it. Again, that's my exponent right there. There's my base, it's base e. So I want to get that green thing by itself. So to do that, I'm going to subtract the 70 from both sides. Okay, let's bring it over here so we have a bit more room. 100 minus 70, 30. E to the negative 0.046 t. Let's divide both sides by the 142. Okay, which ends up being 15 over 71 as a fraction. E to the negative. Okay, so here's my exponent. Okay, so we have e to the 0.046 t equals 15 over 71. So this is base e. So now we'll come up here and we'll use one of these two methods. We'll either rewrite it as a log or we'll log both sides. I'm going to go to rewrite it as a log. So this would be log base e of the 15 over 71, so that's what I'm taking the log of, equals 0.046 t, because logs equal the exponent. So here's my exponent, that's what the log equals. So I have log base e of 15 over 71. Well, log base e we can just write as natural log, ln, of 15 over 71 equals negative 0.046 t. Kind of squished over there. So I have to divide both sides by the negative 0.046. So then t is going to equal the natural log of 15 over 71 divided by a negative 0.046. Okay. Or this is the same as 1 over negative 0.046 times the natural log of 15 over 71. Which then I could put this in here as the exponent on that, but I'm thinking an approximation will be sufficient. So I need to take 1 divided by negative 0.046 and multiply that times the natural log of 15 over 71. and we get 33.8, and this is in time in minutes, 33.8 minutes. Okay, so it will take 33.8 minutes for this to cool from 212 to 100 degrees in a 70-degree room. Okay. All right. Next, logarithmic equations. Okay, we're going to do these very similarly to our exponential, because again, remember, logs equal exponents. Okay, so a logarithmic equation, again, is just a equation. Again, it's an equation, so it has an equal sign that involves logs of variable expressions. So I have a log of a variable expression. For example, log of x equals 12. Hey, so it has a log, a variable in it, and again, we're trying to find what value of the variable makes the equation true. Just like on this side, we had the equality property for exponential equations. They're only equal if their exponents are equal. We have the same for logs. Two logs are equal if they're, again, the same base. Log base b of x equals log base b of y, if and only if, again, that x equals that y. So the easiest way of solving these is if you have two logs of the same base. Here we have the natural log of 4x minus 7. Again, it's the natural log of that whole piece. This whole thing is what's inside the log, because it's in parentheses, equals the natural log of x plus 5. Again, this whole thing is what's inside the log. And these are both base e. They're both base e. So the only way these two can be equal is if this 4x minus 7 equals x plus 5. Okay. And then now we can just solve this like we solve our linear equations. Subtract x from both sides. 3x minus 7 equals x plus 5. Oh, x is gone. Equals 5. Add the 7 to both sides. 3x equals 12. Divide by 3, x equals 4. So now we can double check this. If I take the natural log of 4 times 4, subtract 7, I get that. If I take the natural log of 4 plus 5, same thing. Okay, so we end up getting the exact same thing there. Okay, all right. So that again, that's the simplest way of dealing with it. Okay, the next one is if I don't have a log equals a log. I just got a log equation. Again, this has two different ways of doing it. Okay, the first way is the same here. Here we took the exponential and rewrote it as a log. Here, we're going to take the log and we're going to rewrite it as an exponent. Okay, so we're going to take this log equation and rewrite it as an exponent. Well, it's base 2, so we've got base 2. And logs equal exponents, so this here is my exponent. So 2 to the third is going to equal this guy, 5x minus 17. Well, oh, that should be a 3. Typo on my part, 2 to the third. Well, I can figure out what 2 to the third is. 2 to the third is 8. 8 equals 5x minus 17. Okay, now just solve this like we've been solving. Let's add the 17 to both sides. Okay, we end up getting 25 equals 5x. Divide both sides by the 5. X equals 5. Okay, so x equals 5. Okay, and then we can go ahead and check that. Log base 2 of 5 times 5x. So this one's a little harder to check because it's base 2, and we can't really type base 2 in our calculator. We can go 5 times 5 minus 17, which is 8. So 2 to the third equals 8. Sure does. It worked. Okay. All right, so that was rewriting as an exponent. Our other way is to exponentiate both sides. Oh, both sides. Meaning, make both sides exponents. Meaning, make this an exponent of base 2 and make this an exponent of base 2. Meaning, base 2 to this power. So make this now an exponent. Log base 2, look at how tiny I wrote it up here. Log base 2 of 5x minus 17 equals, not log, sorry, 2 to the log base 2 of x minus 8 equals 2 to the third. Notice where my parts of my equation are. There's the one half of my equation, there's the other half. I just made them both base 2. Base 2, base 2. Because this 2 to the log base 2, these undo each other, and I'm just left with the 5x minus 17. And over here I'm left with the 2 to the third, which is 8. Do you notice this is the same point we had here? So dot, 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 it's going to finish out the exact same way. Really, it just depends on which way you think about it. Okay. All right. We have one more type of equation. This is when we have two different logs, but you can't set them equal to each other. There's no way of getting them to look like this. This is where we need to use our properties of logs. So our first step here is to use our properties of logs to put them together. Okay, use our properties of logs. So here I'm taking a log base 10 of 2x, this is what I'm putting in the log, and a log of x minus 5, I'm adding them. So if we remember our properties of logs, if I'm adding two separate logs, I can write them together as one log, but then it's going to be the multiplication of these two things, 2x times x minus 5, still equals 2. So now I need to distribute here. So now I have the log of 2x squared minus 10x equals 2. So this is log base 10. It's a little 10. So now I'm going to rewrite it as an exponent. So this would be 10 to the second equals 2x squared minus 10x. If I rewrite this log as an exponent. 10 to the second equals this guy. 10 to the second is 100 equals 2x squared minus 10x. Okay. So now I have an x squared and an x, so I'm going to subtract the 100 from both sides. Okay. So then I'm left with 2x, let's move this up a little bit. Left with 2x squared minus 10x minus 100 equals 0. Well, all of these are even, so I'm going to divide both sides by 2. X squared minus 5x minus 50. Okay, I think this will factor, because we've got an x squared, so we'll factor it, x and x. Multiplies to give me negative 50. I add, I get negative 5. 5 and 10 minus 10 plus 5, I think. X squared plus 5x minus 10x. Yep, that will work. So x minus 10 equals 0, or x plus 5 equals 0. We add this 10 to both sides. X equals 10. Or x equals negative 5. Now, always double check them and make sure they work. Because you have to be careful, because we know you cannot take the log of a negative. Okay. So if we look at this, this is taking the log, it's base 10, so I can type in my calculator, of 2 times x, so that would be 2 times 10. Plus the log of 10 minus 5, and it should equal 2, which it does. But when I do negative 5, the log of 2 times negative 5, plus the log of negative 5 minus 5, error, non-real answer, because I end up taking the log of negative 10 right here. So this one does not work. Again, that's what we call an extraneous solution. So it does not work. So x equals 10 was our only solution there. Okay. All right, so next we have our solving exponential and logarithmic inequalities. Okay. Basically, there's no real difference with inequalities, except the only real difference is be careful if you multiply or divide both sides by a negative. Again, remember you have to flip the inequality, flip it. Okay. And the other thing is make sure you don't switch up. Don't switch up the sides. What I mean by that is with an equality, we can very easily flip-flop what's on one side, what's on the other, because it's an equals, it doesn't matter. Okay. We can't do that on an inequality, so I would really encourage you not to rewrite it as an exponent, because we normally tend to flip-flop the sides when doing it that way. So I would highly encourage you to just exponentiate or log both sides. Okay, on how to solve these. Okay, so for this first one, I'm going to do a couple examples here, just the two, and then we'll be done. I know it's getting kind of long. Okay, we have 3 to the x is less than 20. So this is base, first of all, this is an exponent, base 3. So to get rid of an exponent base 3, I need to log both sides base 3. So we'll log base 3 of 3 to the x is less than log base 3 of 20. So this log base 3 of 3 to the x undoes each other, so I'm left with x is less than log base 3 of 20. Okay, so there I'm basically done. X has to be less than log base 3 of 20 because I've got an x over here by itself. This has no variables in it. We could do an approximately. To get the approximately, again, this is the same as taking the log of 20 divided by the log of 3. So x has to be less than approximately log of 20 divided by log of 3. Has to be less than 2.73. Okay, again, this one right here is exact, right there. This one here is approximately, right there. Okay, so x has to be less than log base 3 of 20. Okay. All right, and let's do another one here. So now let's do a log one. Again, this is a log base 10. Base 10. So to get rid of it, I'm going to exponentiate both sides base 10. So I'm going to take 10 to the log of x is less than or equal to 10 to the second. So again, here we're both base 10. These now both become exponents. Since this is base 10, these two undo each other. So x would have to be less than or equal to 10 to the second, which is 100. That one's a whole lot easier to do. So x would have to be less than or equal to 100. Okay, you might be like, woohoo, that was easy. We're done. Okay, but we have to be careful because you cannot take the log of a negative. If I think of all the numbers less than or equal to 100, that includes some negatives. And this was a log equation. This one wasn't, so you don't have to worry about it. It was an exponential equation. This one was a log equation. If I think of all the numbers less than 100, it's all of these. Eventually we're going to hit 0 and we're going to get some negatives. I can't take the log of a negative. So meaning I have to stop here at 100. So I'm just looking at the numbers in between 0 and 100. So I'm going to have to stop at 0. So I'll have to say x is also going to have to be greater than 0. And we can't equal 0 because we can't take the log of 0. Okay? So we're going to have to be greater than 0. So I could write it as two separate things, this and that. Or we could write it as 0 less than x less than or equal to 100 as one compound inequality. Okay. All right, so there is our solving inequalities. Okay. All right, good luck.